Hello guys, welcome to my YouTube channel. My name is Lakhani Manav. I am a student of Charusat University. My enrollment ID is 24CS047. Today I will go to explain temperature controlling fan using logic gates. A temperature controlling fan is a system that automatically adjusts fan operation based on temperature level. Instead of using microcontroller, this project is designed purely with logic gates to demonstrate digital logic application. It operates by comparing the temperature from a sensor with a threshold and activating the fan accordingly. This system is reliable, cost effective, and power efficient, making it useful in automating cooling system. Key features of a temperature controlling fan. It fully digital implementation using logic gates, no microcontroller or programming required. Use a comparator circuit for decision making, suitable for educational and practical applications. Now we see the objectives of temperature controlling fan. To design a fan that operates automatically based on temperature, to utilize logic gates instead of a microcontroller for decision making, to optimize circuit efficiency with minimal noise interference, to reduce power consumption while maintaining performance. Now we see the component required for build temperature controlling fan. First sensor and comparators, second logic components, and third one is passive and power components. First, temperature sensor and comparator. Temperature sensor sense temperature and provide an analog voltage out. Comparator compares the temperature sensor output with a reference voltage. Logic gates used to process comparator signal and control fan operation. Transistor act as a switch to control the fan, and PWM circuit controls fan speed. Resistor used for voltage division and pull up pull down function, also for and reference voltage. Fan represent the cooling mechanism. Power supply 5 volt to 12 volt power the entire circuit. Breadboard and superwires for circuit assembly. Now we see one by one all the components. First is temperature sensor, TMP36. It converts temperature to an analog voltage. Output voltage is 10 millivolt per degree. Operating voltage is 2.7 volt to 5.5 volt and accuracy is plus or minus 1 degree typical. Why we use TMP36 sensor over the other sensor? Because no external calibration required, lower power consumption than thermistor, more accurate than LM35 for low temperature applications, works with a single power supply, wide operating range compared to LM35. And you see the diagram of TMP36 temperature sensor. First pin is represent VCC, second represent V out, and third one is represent ground pin. Now you can see the comparison between TMP36, LM35, thermistor and thermocouples temperature. These are different temperature sensor and you also see advantages and disadvantages of them. Now we're going to see noise factor of temperature sensor. Prone to environmental noise from electrical interference, require proper grounding and shielding for accuracy. And response time of TMP36 temperature is 1 to 2 seconds. And second component is LM339 low power quad voltage comparator. It contains four independent voltage comparator in a single package. It operates on single or dual power supply. It allows multiple configuration. Its application are voltage sensing, zero crossing detection, and analog circuits. Why we use LM339 sensor instead of other sensors? So reason is it operates efficiently on low voltage. It provides wide supply voltage range. It works with 2 volt to 36 volt supply and contain 4 comparator, reducing circuit complexity. And it can interface with different logic families and drive loads. The LM339 also offers high stability and accuracy, ensuring precise voltage comparison and low input offset voltage which reduce error in single detection. Now you can see the LM39 pin configuration block diagram. Here first is VCC pin number 3 for power supply, and ground connection is pin number 12, and comparator inputs are inverting inputs pin number 4, 6, 9 and 11. It used for reference voltage. Non-inverting inputs is used for input signal voltage, and pins are 5, 7, 8, 10, and comparator output pins are 1, 2, 13 and 14. It's for open collector outputs for each comparator. Now we understanding inverting and non-inverting inputs. First is non-inverting inputs. When high voltage here makes output low, and when higher voltage here makes output high, is the application of inverting input. Comparator function is it compares inverting and non-inverting input and switch the output accordingly. Now we see LM339 circuit working principle. First, it compares two input voltage at its inverting and non-inverting terminals. If the non-inverting input voltage greater than inverting input voltage, then output is high and open collector floating. And if the non-inverting input voltage less than inverting input voltage, output is low, sink current to ground. The open collector output allows the user to connect an external pull-up resistor to define high voltage. Here you see different comparator like LM339, LM393, LM348, and OP08, and also see supply voltage, output type, number of comparator used in sensor, and special features of all sensor respectively. And now we see comparison of LM339, LM393 and LM358. So first comparison is LM339 versus LM393. LM339 has 4 competitors, LM393 has 2 competitors, and LM339 versus LM358. LM33 has open collector output, whereas LM358 has push-pull. When to use LM393? When multiple voltage comparison are required in a single IC. We are going to see application of LM339 comparator. It zero crossing detector detects SA signal. Zero crossing. Second is voltage error detection. It detects over voltage or under voltage condition. Now third one is sensor interfacting, used with temperature, IR or LDR sensor. Fourth one is schematic trigger circuit, convert noisy signal to stable digital output. Now we see LM39 in temperature controlling fan. So temperature sensing, compare voltage from temperature sensor, and if temperature exit threshold and fan is turned on, and fan deactivation when temperature drop, fan is turned off. And efficient control provide an efficient way to control fan speed based on the heat levels. So conclusion is LM39 is a versatile low power comparator. It offers open collected output and operates over a wide voltage range, suitable for application require multiple comparators in one package. Choose one other due to its efficiency, low power, and flexibility. Now, third one is a transistor. So, what is transistor? A transistor is a semiconductor device used to amplify or switch electronic signal. It has three terminals: emitter, base, and collector. Transistors are the building block of modern electronics. There are two types of transistor. First is bipolar junction transistor, or we can say that BJT transistor. And second one is field effect transistor, or we can say that FET transistor. In this project, we use BJT transistor. So types of BJT transistor. Now one first is NPN transistor. Current flow from collector to emitter. The base control the flow used in switch circuit. And second is PNP transistor. It allows current flow from emitter to collector and works opposite to NPN transistor. We use NPN transistor in our project. Why we use NPN transistor? Because easier to control with low voltage, use in most switching application, faster response time compared to PNP, and widely available and cost effective. Now we can see common emitter, common collector, and common base. These are the configuration of a transistor. First is common emitter. It mostly used in amplifier and switches. Second is common collector. It used for voltage regulation. And third one is common base. It used in high frequency application. In this project, we use the common emitter configuration for switch transistor pin explanation. Collector connected the load fan and base control the transistor on and off. Emitter connect to the ground. Why we not use PNP transistor? Here you can requires a different circuit design, more complex switching mechanism, and PNP is more common in low voltage application. Now we're going to see noise factor in transistor. So first is thermal noise. Due to heat in the circuit and short noise for random fluctuation in the current, and flicker noise is low frequency noise affecting accuracy. In this project, thermal noise is the main concern. Timing delay in transistor. Turn on time, time taken to start conduction, and turn off time is time taken to stop conduction, and propagation delay affect circuit response time. NPN transistor have faster switching speed than PNP. Why use BJT instead of MOSFET? BJTs are better for lower power switching. MOSFET are better for high power application. In this project, BJT is sufficient to switch the fan on and off. Now, practical use in our circuit. So, temperature sensing TMP36 sensor measure temperature, and LM339 comparator LM339 compared with threshold and switching NPN transistor switch is fan on and off. In short, transistor control switching in electronics and pen transistor are preferred for low voltage circuit. Our project use a BJT in a common emitter configuration. Now we fourth is logic gates in the circuit. There are seven types of logic gates. Some logic gates that use in our circuit. First is NOT gate, clips LM339 output, and AND gates. It ensure correct logic for fan operation. OR gates, it allow manual override to turn fan on. NAND gates used for PWM based speed controller. Function is process signal to make logic decision. Noise factor of logic gates. Power supply noise can affect logic transistor, and delay of the logic gates in the circuit is logic gates operate at nanosecond speed but introduce minimal propagation delay. It's 10 to 20 nanosecond. Now, table, you see the different status of logic gates like NOT gate, AND gate, OR gate, and also see fan status on or off. Now we're going to understand PWM, pulse width modulation. PWM is a technique used to control power or signal strength by varying the duty cycle of a periodic signal while keeping the frequency constant. Key concept of PWM is it instead of reducing the voltage directly, PWM repeatedly switch the power on and off at the fast rate. The average voltage deliver depend on the duty cycle. And example, if a PWM signal has a 50% duty cycle, the output is on for half the time and off for half the time. If the duty cycle is 75%, the output is on for 75% of the cycle and off for 25%. Why is PWM used? PWM is widely used because it provides efficient power control, so no energy loss as heat, unlike resistor, and smooth speed control like fan for fans or motor. precision signal modulation for audio and communication, dimming of LEDs for variable brightness controller, and power conversion for DC-DC, inverter, and power supplies. How PWM work? Here you can see the duty cycle 0%, 25%, 50%, 75%, and 100%. And also see the deliver power and effect respectively. When 0% duty cycle, power delivery is 0% and effect is no power consumption. And when duty cycle 25%, power delivery 25% and effect is low power consumption. And when duty cycle is 100% and power delivery is 100% and the effect is uh, fan is fully on. PWM signals consist of repeat on and off pulse at a fixed frequency. Here you show the key equation of duty cycle. Duty cycle equal to T tone by tone plus tau into 100, where T on equal to time where the signal is high and T off is where time when the signal is low. Now implementing PWM in different method. PWM using 555 timer IC, best for basic PWM control, low cost application, and working the capacitor charge and discharge to control T on and T off. R1, R2, and C1 determine the duty cycle. Formula is T on equal to 0.693 into R1 plus R2 into C1 and T off equal to 0.693 into R2 into C1 and frequency is count by 1.44 by R1 plus 2R2 into C1. Why we use 555 timer? It cheaps and simple, no programming required, easy to adjust duty cycle. PWM using microcontroller and OPM. PWM using microcontroller. Best for digital control and high precision. Working of PWM using microcontroller. Use time modulation inside microcontroller. To get generate PWM can be controlled via code. Example analog write in Arduino and advantages are very precise, easy software adjustment and can generate multiple PWM signals. And PWM using operator amplifier. It best for analog PWM generation. Working is a triangle wave is compared with DC reference voltage. When the triangle wave exceeds the reference, the output is high. Why use OP-amps for PWM? It useful in analog circuit, can be used in power inverters. Application of PWM in real world electronics. First is motor speed controller, second is LED dimming and display brightness, third is audio signal processing, fourth is power electronic and inverters. Advantages and disadvantages of PWM. Here are few advantages of a PWM. You can see first is very power efficient, no heat dissipation like a resistor, provide precious control over power and speed, wide application from audio to motor control, simple to implement with a 555 timer or microcontroller. And disadvantages is generate high frequency noise, interference, high speed switching can cause voltage spikes, require filtering for smooth analog out. Now we see the comparison between PWM and analog controller. Why PWM is better? So you the see comparison between PWM and analog. There are PWM controller and analog controller. You see the features, efficiency, precision, speed controller, power consumption, and complexity. PWM is a preferred method in modern electronic because it is efficient, precise, and widely used in digital system. How to fully optimize a temperature control fan using PWM. So first is optimize fan perform with PWM. Use high frequency PWM above 20 kHz to avoid Audible noise. Choose a MOSFET instead of VGT for faster switching and higher efficiency. Implement a lower power filter to smooth PWM output if need. Use temperature feedback with a sensor like TMP36 and adjust PWM accordingly. How PWM is used in temperature controlling fan. Here you see the implementation of PWM in our temperature controlling fan. So temperature controlling fan detect temperature, comparator compares with set threshold and PWM generate PWM signal. Transistor switch the fan on and off based on PWM and fan run at variable speed based on temperature. So conclusion of why we should use PWM in our circuit. Uh, Efficient power controller, precision speed and brightness control, versatile application and easy to implementation. PWM is the backbone of modern electronics, making everything from motor controller to power conversion more efficient. Here all components are done and we see step by step wiring and connecting guidance. Here you see first you connect temperature sensor to comparator. The TMP36 sensor outputs a voltage that change based on temperature. This voltage is compared with a reference voltage using LM339. The comparator output will be high if the temperature exceeds the set threshold. Reference voltage setup for a comparator. So we use 10 kilo ohm resistor to 5 volt to LM39 inverting input pin number 4. Second register of 10 kilo ohm between LM39 pin and ground. These provide a 2.5 voltage reference voltage. LM39 output pin number 2 goes to logic gates if TMP36 voltage greater than 2.5 volt. LM335 output equal to high and if TMP36 voltage is less than 2.5 volt, LM39 output low. Now we see the implement logic gates in our circuit. So first is not gate LM339 output pin number 2 not get input and not get pin number 2 of not get output. It connect to the AND gate and ensure proper logic signal polarity for the next stage. Now we see the implementation of AND gate. So input pin 1 is connected to the NOT gate output and second input pin is connected to the LM339 output and gate output is pin number 3 is connect directly to the OR gate and ensure the fan turn on only when the temperature is high. OR gate. First pin is connect to the AND gate output. Second pin is connect to the manual switch. Connect to the 5 volt when press. OR gate is output. Pin number 3 is directly connected to the NAND gate. It allows manually control of the fan even if the temperature is low. PWM generation. Uh, NAND gate pin number 1 and 2 is directly connected to a 100 kilo ohm resistor and 10 microfarad capacitor. And pin number 3 of NAND gate output is directly connected to the NAND gate 2 input pin number 4 and NAND gate to output pin number 6 is directly connected to the fan control transistor based via 1 kilo ohm resistor. Now simple PWM generation that control fan speed based on the temperature. Now we see the implementation of transistor switching the fan on and off. So here you see the pin configuration and base connect to the PWM output, collector is connected to the negative terminal of fan and emitter is connected to the ground. Since logic gate cannot directly power the fan, we use transistor as a switch. Now you can see why we use NPN transistor instead of a PNP transistor. We already discussed about it and fan connection is fan positive terminal as connect to the 12 volt power supply and negative terminal as connect to the collector of transistor and also we need a power supply of 5 volt for logic gates and TMP36 sensor and 12 volt for fan. So final circuit diagram is temperature sensing. TMP36 output voltage based on temperature. comparison LM339 compare with reference voltage, logic processing, not and NAND gets processing signal, fan controller, transistor switch, fan on and off with PWM speed controller. Here is the complete connection flow. Why I explain you. If temperature exceeds threshold, fan turn off, PWM control speed, and if temperature drops, fan turns off. Now we see the basic diagram of temperature controlling fan. Here you see the circuit diagram. TMP36 temperature is directly connected to the LM339 converter via reference voltage between 2.2 volt or 2.25 volt, and it connect to the logic gates for manual override, and then PWM generate by NAND gate, and then you can see the when we turn manual override, then our output is high and reference voltage is 2.2 volt and temperature is 45 degree. Now we reduce temperature, you can see the speed of fan is decreased, and where I increase the temperature, then you can see the speed of fan is also increased. So these are the basic block diagram of a temperature controlling fan. Why is this fully optimized by logic gates? So no microcontroller required, everything is done by using simple gates. PWM also smooth fan speed control. PWM provides variable speed without complex programming, and directly button control by passes automatically system where need. NPN transistor provide clean switching with minimal power loss. At the last, we see final summary of a temperature controlling fan, and also we see the comparison between logic gates and microcontroller if we use in our temperature controlling fan. So here final summary is temperature measurement. TMP36 measure temperature and give voltage output. Voltage comparison. LM339 compares this voltage to a reference voltage. Logic gates process the comparator output to control the fan. PWM using NAND gates enables speed control. A transistor switch the fan on and off based on logic output. Here you see comparison with microcontroller based approach. So here you see if we in logic gate circuit complexity is moderate and in microcontroller complexity is high, and cost of logic gates is low and microcontroller is high. Speed control by PWM in the logic gate circuit and speed control by software based in microcontroller, and power consumption in logic gates is low and power consumption is higher in microcontroller. So in the last conclusion, our circuit is fully optimized by digital circuit using only logic gates, efficient fan speed control using PWM technology, and expandable design for advanced applications like AC fans or multiple sensor. So thank you for watching this video.